Okay, so we are going to talk today about rational functions and graphing them. And so we're going to talk about the domain, range, symmetry, and behavior, intervals of increasing and decreasing, and all of that of rational functions. So functions that can be written as a fraction. This video might come in two parts. It depends how long it takes me. So we also wanted to determine transformation so we can sketch graphs without graphing them in your calculator. So we are trying to write equations of a given graph and graph rational functions without a calculator today. So first of all, just talking about the parent function of a rational function. So the parent function would be 1 over x, and the function accepts all real numbers except 0, because 0 is the only number that x could not be equal to, because division by 0 is undefined. So you can't have a 0 in your denominator, therefore you can plug in any other number except for 0. If you wrote that as an inequality, it would mean that x is greater than 0, or x is less than 0, or x is greater than 0. If you wrote it in set notation, it would be the set of all x's such that x cannot be equal to 0. And in interval notation, it would go from negative infinity to 0 with a parenthesis, union, 0 to positive infinity. You don't have to write the plus sign on the positive infinity. It's just there for that one. So the end behavior comes from, we're going to look at what actually happens. So this is like a little XY table. So x increases without bound. That means we are plugging in a number for x that is continually getting significantly larger. So we're plugging it into 1 divided by x. So in a calculator, if you go 1 divided by 100, you would get 0.01. So we would have 0.01. And then if we divided 1 by 1,000, similarly we would get 1 divided by 1,000, which is 0.001. And if you get the gist of it, you would get 0.0001 for 10,000. So as you increase your x's, like as your x's go to infinity, the function is going to 0. It is getting closer and closer and closer to 0. So when we plug in the negative of those numbers over in the second table, we get the same numbers. We get negative 0.01, well the same numbers but opposite, negative 0.001, and negative 0.0001. So that is also approaching 0. So this is the first time that we're going to have something that limit is not approaching infinity or negative infinity. It is approaching the number 0. So as x approaches positive infinity, f of x is going to 0. And as x approaches negative infinity, f of x is also going to 0. So in limit notation, we would say the limit as x approaches positive infinity of f of x is equal to 0, and the limit as x approaches negative infinity of f of x is also 0. So there are two different notations for writing limits. We're going to usually use limit notation. Okay, so then let's look at it as we go the opposite direction. So that one we were plugging in numbers that were approaching infinity, like 100, 1,000, 10,000. Now we're going to plug in numbers that are small, that are approaching 0. So these are going to be a new kind of limit. They're limits as we approach 0, not as we approach infinity. So as we approach 0 from the positive direction, so if we're coming from the right and like moving left towards 0, that would mean us plugging in these particular values for 0. So 0.01, if we plug that into our calculator, then we would get 1 divided by 0.01 is going to give us 100. if we plug in 0.001 and we got 1 divided by 0.001, that would give us 1,000, and continually it would get bigger. So this, if we plug in 0.0001, we would get 10,000. So our numbers are now approaching infinity as we get smaller and smaller. So as we plug in smaller numbers for x, as our x approaches 0, our y values are approaching infinity from the right. So if we go from the positive direction, so that's going to give us infinity here. And then if we plug in the negatives, it just changes the values. So it would just make these negative 100, negative 1,000, and negative 10,000. So instead of it approaching positive infinity, as we approach it from the left, so as we're coming from negative infinity coming towards 0, so going to the right, then our limit is approaching negative infinity. So in limit notation, we would write the limit as x approaches 0, and then we're coming from two different directions. One, we're coming from the right, so we put a positive on it. That is equal to, of f of x, is equal to positive infinity. And then the other one, the limit as x approaches 0 from the left, so you put a negative after it, of f of x, is equal to negative infinity. So we're going to look at the graph in just a second to see where this is going, but this is the end behavior depending on what we're approaching. So we can have end behavior when we're approaching infinity on the x-axis, and we can have end behavior as we're approaching x values. So the behavior of our graph near 0 indicates that the graph of f of x approaches but does not cross the x or y axis. So that axis is an asymptote for the graph. So we're going to talk about domain and range now. So domain we already talked about. We're going to talk about range. So our range is the y values. And if you notice, if you can plug in any number for x besides 0, and your y values would be any number except for they would never be equal to 0 because you have a 1 in the numerator. So since we have a 1 in the numerator, you can't divide 1 by something and get 0 as your result. So the function takes on all real numbers except for 0. So the function's range is as follows. You could either write it as an inequality, so y is greater than 0, or less than 0 or greater than 0. You could write it in set notation, so the set of all y's such that y cannot be equal to 0. And in interval notation, where the symbol u means union, negative infinity to 0 with a parenthesis, union parenthesis, 0 to positive infinity. So the domain is every number except for 0, and the range is also every number except for 0. So I know on here it says function booklet. Ignore that. That's from last year. But we are going to draw the parent function in here, and you need to know this function. You need to know this parent function just like you know the parent function for a parabola. So our equation is f of x is equal to 1 over x, and the graph, if we plugged in 1, just to kind of get an idea, we could graph this in your calculator and draw from there. But if you plugged in 1 for x, you would get the value 1 back. 1 divided by 1 is 1. So we know it goes through 1, 1. And then if you plugged in negative 1, you would get negative 1 back, so we know it goes through negative 1, negative 1. So I'm going to plot those 2 points as my reference type points, and then talk about the rest of it. So I already talked about the domain. So the way we can write it is equal to all real numbers except x cannot be equal to 0. And the range is also all real numbers except x cannot be equal to 0. And you can write that in formal set notation or in interval notation. It is and then let's draw the graph. So it has an asymptote, which is going to be denoted by a dotted line on the x-axis and also on the y-axis. So it is not going to cross the x or y-axis. And if I plotted like the other points that I got, so we said that our limit as x approaches infinity was 0, well, sorry, not limits. Let's look at this. I'm just going to draw the graph so you can see it, and then we'll talk about the values of it. So it technically it's coming and approaching here, then it jumps down and approaches 0. So it never actually touches the asymptotes. And then we have, it starts again really steep coming in and then goes down. So we have horizontal and vertical asymptotes here. So this is our parent function of a rational function. And if you look at it, it is increasing never. As we go from left to right, the y values are always decreasing. Even when it jumps, it's still not decreasing. So it is never it's never increasing. So it's never decreasing, meaning it is always decreasing, except for on the y-axis, so where x is equal to 0, nothing is happening. So it's decreasing from negative infinity to 0, with parenthesis, union, parentheses, 0 to infinity. And the left-in behavior, so as we move to the left, that limit is approaching, so as we're coming to the left, that graph is approaching 0, but doesn't actually touch 0. That's our y value. So our left-in behavior, we would write the limit as x approaches infinity of f of x is equal to 0. Oh, sorry, negative infinity. And the right-end behavior means as we move into the right, where is our y value going? Our y value is also going to 0. So the limit as x approaches positive infinity of f of x is also equal to 0. And then is this function even or odd? So remember, odd is when you could fold it on the x-axis and the y-axis and still get the same graph. And so it is actually an odd function. So it is odd. The x-intercepts, well, it never crosses the x-axis, so it never has an x-intercept. It never has a y-intercept either. And it has no minimum or maximum value. Is the function one-to-one? As you go, does it pass the horizontal and vertical line test? Yes, it is a one-to-one function. And then here's where we get into these asymptotes and discontinuities. So we have an asymptote or discontinuity on the line x equals 0 and on the line y equals 0. Those are both of our asymptotes. And the asymptote behavior, which is not the end behavior, but the asymptote behavior, so what's happening at those asymptotes, is as follows. So we would have the limit as x approaches 0 from the right. So as we're approaching 0, just so you can see it with this yellow here, as we're approaching 0 from the right. So as x is approaching 0, that would be us coming right here. As it approaches 0, our graph is shooting up and is approaching positive infinity. So the limit as x approaches positive or 0 from the right for our function f of x is equal to positive infinity. And then similarly, the limit as x approaches 0 from the left, which is why we have that negative there, of f of x. If we look at this yellow line, as we're approaching 0 from the left, our graph is shooting down, so it's approaching negative infinity. So that is the first parent function that you need to be aware of. And the next parent function is 1 over x squared. And I'm going to pause here and go to a new video.